Hey, this is the video, Introduction to Structural Member Properties. Really what we're talking about is beam deflection. So we're talking about beam deflection. Okay? All right, so when we're talking about beam, one of the big things that we're going to be talking about is the moment of inertia. Okay, basically, the moment of inertia gives you information about how the cross-sectional area, right, so remember we were talking about if you cut something in half, you would get the shapes like this, and then they had the C channel, right, how it will be distributed across the centroidal axis. Remember, centroid is the center of an object, okay? So we're concerned with how stiff that object is. So it's the stiffness of an object related to its shape, okay? So the higher the moment of inertia, okay, the greater resistance it has to deformation. So that means that the higher the number, the less likely it is to get deformed, okay? All right, so here we have two beams. We've got A, which is a joist because of the way that it's positioned, and B, which is a plank. Now, if you notice, if we're looking here at their dimensions, the dimensions are the same with the difference of the width and the height being switched because of the orientation of the beam. The area is the same, okay? So when you look at that, if you think about them both being on supports, and then let's say somebody stands on it that weighs 140 pounds, 140 pounds. Okay, which one is going to bend more? Okay, so if you really think about it, A is going to bend just a little bit. You know, it's going to give a little bit of deformation because you're adding weight to it and it's not a piece of metal, which would be even higher. And B is probably going to bend a lot, okay? Okay, so this one's asking basically what I just said. The thing that's different about these two is the way that they're positioned, okay? So think about it. All of the force here is going across this, which is the reason why it's bending, whereas this one, all of the force is going across this, right? So that's creating more of a resistance, okay? So that means that A should have a higher moment of inertia than B. Okay, so we're going to go ahead and calculate the moment of inertia, and then we're going to just use rectangles. So what this means is the moment of inertia is equal to the base times the height cubed and then divided by 12, okay? And this being the base right here, and then this being the height. Okay. So when you're talking about beam A, this is your base, and this is your height here. And if you notice, the height is being cubed, okay? So this is the algebra that goes along with it. You guys can all plug that in. So you've got 5.5 cubed, which is going to give you this 166. So that gives you a moment of inertia of 21 inches to the 4th power. Now when we do beam B, it's going to be laid on its side, right? So now our height is only 1.5 inches. So 1.5 is the number being cubed, which means that it's going to be a smaller moment of inertia, which makes sense, right? Because when it's laying flat like that, you have less resistance, okay, to what you're doing, to putting that weight on top. All right, so basically what it's saying is that if beam B is 1.5 and beam A is 21, that means that beam A is 14 times stiffer than beam B. Okay, so if you wanted to something to not deform, you would want to position it in this fashion. Okay, so if you ever see buildings, like especially big skyscrapers, they don't typically use just flat objects, right? You guys learned about these in the last note. So you have the I-beam, the C-channel, the box, the angle, and then this is a solid piece, so a plank. Okay, now finding the area and the moment of inertia and things like that for complex shapes, we're not really going to be doing that, but I just want you to look at something. Okay, so it's got the same heights, right, the same heights, and it's got the same widths. Okay, now this moment of inertia is higher than this moment of inertia. So obviously this one is going to have, so this one is going to have less deflection, right? It's not going to move as much. But look at the difference in the areas. You've got 8 as opposed to 2.7. Okay, so basically what you're doing is you're doing more with less. Because if they built buildings out of just straight steel, buildings would be very, very expensive. So this gives you enough resistance to deformation while saving you enough money to where it makes sense. So sometimes a lower number is better, just depending on what you're wanting. Okay? All right, so the next thing is talking about the modulus of elasticity. Okay? So this is a ratio of the form of stress is related to the form of strain. It's basically saying it's defining the stiffness of an object related to its material chemical properties. Okay, so we're talking about its chemical makeup. And just like the moment of inertia, the higher the modulus of elasticity, the greater it is to resist deformation. Okay? All right, so we have 2 planks here again, and we've got A and B. And if you notice, A is made of Douglas fir, and B is made of plastic. They're both situated in the same way. They're both standing upright with their their heights being here. This one's made of wood, A is made of wood, and B is made of plastic. So just by thinking about what you know, which one would be less likely to be deformed, right? Okay, so they're just asking you the same thing. We're putting the same load. So if we had them sitting on things here, right, which one would bend the least? Now, if you don't know this, wood would actually be stronger than plastic, okay, because it has a higher modulus of elasticity, okay? All right, so basically all it's saying is that B has got a lower modulus of elasticity than A. Okay, so what it means is it's able to pop back. Like, think about elasticity as being elastic. So basically, the more you bend it, it's going to go back into shape. Whereas plastic, if you're bending it, the more you bend it, it's going to stay in that shape. Whereas wood is going to tend to go back to where it goes. Okay, so this is going to be what we're going to talk about. All right. All right, so here is our formula. Now this triangle is supposed to be upright. All right, so F, this is the force that's applied. So this is the force. The L is the length of the object, and just 48 is the constant. E is the modulus of elasticity. Okay, they give you that. You don't have to know that, okay, unless they give you everything else and you're trying to look for that. But that's a number that is there. And then I is your moment of inertia. Okay. All right, so when they did beam A, they came out with their max. Okay, and then they do beam B. Okay. Okay, now once you do your calculations, you're going to find that the modulus of elasticity of, or your max amount is going to be higher for A than it is for B. So it's really just a matter. It's just a matter of plugging in the formula and seeing which one has the highest number. All right.